Today we are going to be doing a little progress update on the 4-bit computer that is based loosely on the CHUMP build with some modifications, of course. So for the power supply, we have a USB cable that I cut off one of its ends, stripped the power wires, and then I connected them to the positive and negative parts. These two are shorted and these two are shorted. And then we also have a capacitor of 220 microfarads in parallel. Basically it goes like this, and this is on the breadboard, and I can use one of these portable batteries to power it. And here I can turn on the automatic clock, and you can already see some stuff happening. So yeah, let's look at the build. First, right here we have the clock module. First you'll see right here that we have two 555 timers. One in astable, this right one, and one in monostable mode. This LED right here just shows the clock, the raw clock output of the computer. And then these 4 bits show the program counter. Anyways, so right here you can see the monostable and astable controlled by this button. And of course, there's a decoupling capacitor on each one of the chips, as well as a decoupling capacitor for the clock signal itself, just to make sure that we have clean edges. This right here is the program counter chip, 74-161. And it's actually feeding the address into the ROM, which we'll look at later. And then right here, we have a dual edge triggered data flip-flop, which I'm gonna use for essentially dividing the clock so that I can have multiple instructions happen in between lines of code. And then here I just have some chips to help me with that, an AND gate and an OR gate, which I'm gonna use later for the opcode decoding. Next, we're going to look at the ROM, which basically has the constant as the first 4 bits and the opcode as the second 4 bits. So here we have a 3-bit decoder, 3-to-8 decoder. And you can see it takes the 3 bits of the opcode and decodes them. Here we have the 74-189, which is the RAM chip, which holds 16 addresses, each with a 4-bit number. And just an inverter here to invert the outputs because the outputs are inverted. And here we have the essentially multiplexer that I don't have a chip for it, so I have 2 of these bus drivers with tri-state outputs. And I switch, you see that they're both connected with their outputs. And this is essentially the multiplexer for the computer. And I have here an inverter so that their enables are flipped, so only one is enabled at once. They control one of the inputs, the A number input for the ALU, which right here I have constructed. It's just 4 full adders in a ripple setup. Right here you can see we have 2 AND gates, then 2 XOR gates, and 1 OR gate. So now let's look at what I'm going to do next. I'm going to add accumulator. For the accumulator, I don't actually have a proper chip for it, so I'm going to use one of these 74-161s. And so basically what we'll do is, because it always adds to itself, first we'll clear on one of the intermediate clock pulses. You can see I have here 3 clock pulses between the actual next line. And then we're going to set this to add the constant because we're loading in a number set for the load instruction. So we're going to just add, we're first going to clear it, and then we're going to add the constant here through the multiplexer. And of course, any number plus 0 is just that original number. And then we're going to latch it on the other intermediate clock pulse. So I have a bunch of decoder stuff, like say I have an F0 instruction, which is the most complicated one. I'll put an image on screen for the logic circuit itself and how it works. Yeah, it's basically all we have right now, but we'll look at it later when I have built more parts for it, and yeah.